Okay, so we've talked about the reaction of a hydroxyl radical with a number of stable gases that initiate the oxidation process, and then the intermediate radical that formed from that reaction with hydroxyl radical reacted with O2, in many cases to form a hydroperoxy radical that was, and some further oxidation product of the initial starting material. So for example, we took carbon monoxide and we converted it to carbon dioxide, so we fully oxidized it. But then you might be wondering, well, what happens to the hydroperoxy radical? And it turns out that the hydroperoxy radical will react with nitric oxide, which is present in the atmosphere. Nitric oxide is present in low concentrations, but it's high enough of a concentration to make this reaction relevant, and it happens pretty rapidly. And nitric oxide will simply abstract an oxygen atom from the hydroperoxy radical to regenerate hydroxyl radical and to form NO2. And so if we think about this from the perspective of hydroxyl radical, what we can see is we kind of have this catalytic cycle where you start out with the hydroxyl radical. This will react with some stable gas that could be one that has a double or a triple bond, you get addition, or one where you get hydrogen atom abstraction. And then subsequently O2 reacts with that product to form generally hydrogen atom abstraction would generate the hydroperoxy radical. And then that hydroperoxy radical is then turned back over to the hydroxyl radical by nitric oxide. And that regenerates then the hydroxyl radical to undergo this continual oxidation process. So even though the lifetime of hydroxyl radical in the troposphere is extremely short, just about 1 second, it is quickly regenerated by these reactions. And so there's always a steady state concentration of hydroxyl radical in the troposphere. So then you might wonder, well, okay, what happens to the nitric oxide or the nitrogen dioxide that's resulted from this? Because eventually we would just run out of nitric oxide and then we wouldn't have any of that to regenerate the hydroxyl radical. And so it turns out that we can actually regenerate nitric oxide as well. So NO2, if we look at its absorption spectrum, so here nitrogen dioxide, if we look at its absorption spectrum, what we notice is it absorbs UVA and UVB light and even out into the visible region. And UVA light, you'll remember, is not blocked by the ozone layer, and so this penetrates down to ground level and so into the troposphere. And when NO2 absorbs UVA light, it undergoes a photochemical dissociation to split back into nitric oxide and then liberate a free oxygen atom. And so what we see here, if we look at just the nitrogen species, there's also a catalytic cycle for the nitrogen species, for NO and NO2. Take nitric oxide, react it with hydroperoxy radical to generate NO2, which is then photochemically regenerated back to NO. And so at nighttime, what we would see is essentially all of this cycle would rest in the nitrogen dioxide state, since there's no light to dissociate it. But then once we're in the daytime, morning hits, and the sun comes out again, then you get fairly rapid decomposition of nitrogen dioxide back into nitric oxide and liberation of a free oxygen atom. Now, okay, we've talked about catalytic cycle for hydroxyl radical, now catalytic cycle for nitric oxide, but now we've got a free oxygen atom. And so this should be triggering bells in your mind thinking, well, I know what a free oxygen atom does in the stratosphere. It reacts with O2 to form ozone. Well, in the troposphere, the air pressure is much higher than it is in the stratosphere. And so that reaction should occur extremely rapidly, and it does. And this is now where we get regeneration of ozone. So we started the whole process at the very beginning when we talked about the initial generation of hydroxyl radical. That came from trace amounts of photochemical dissociation of ozone. Well, now we've regenerated the ozone. And so we have kind of this multiple set of cycles here. We've got all of these different reactions that are constantly going on and cycles that are constantly going round and round And with the net result that we are oxidizing any species that's only partially oxidized or even fully reduced in the atmosphere. So let's put all of this together into one kind of large catalytic cycle here. So if we start with hydroxyl radical as the main species, the one we focus on, and it kind of kicks off the whole sequence, what I can note is if I just take carbon monoxide as an example, and this is just an example that it could react with any other number of species, but if it reacts with carbon monoxide, we generate this initial transient carbon-centered radical, but via addition of the hydroxyl radical to the carbon-oxygen triple bond to then form a double bond and then radical on carbon. This intermediate radical is now very reactive and so reacts with diatomic oxygen or molecular oxygen, and that does a hydrogen atom abstraction and oxidizes this species up to CO2, and that leaves you then with the hydroperoxy radical. This hydroperoxy radical is turned back over to hydroxyl radical via reaction with nitric oxide. So nitric oxide comes in, pulls off the oxygen atom, that will generate nitrogen dioxide. Both of these don't have a full octet, so there's actually a radical centered on nitrogen in these. But then NO2 we know is turned back over photochemically to generate nitrogen, nitric oxide, and then a free oxygen atom, which I've just drawn here. I haven't drawn all of the valence electrons, but it's got 2 unpaired electrons in its just atomic Lewis structure. And then this oxygen atom reacts with just molecular oxygen to regenerate ozone or generate an equivalent of ozone, which under certain cases, when the UVB light penetrates down to ground level, and there's always some fraction of UVB light that makes it down, but that depends on the concentration of the ozone layer in that particular region. But eventually you'll get trace amounts of this that will absorb UVB light and then undergo photochemical dissociation to regenerate an oxygen atom, but now it's an excited oxygen atom. That excited state oxygen atom will react with water vapor that's in the air to essentially regenerate hydroxyl radical and generate another equivalent of hydroxyl radical. So these are the many processes that are going on. There's a net oxidation that's occurring from CO here up to CO2, or if this was a hydrocarbon, we would eventually end up at CO2 with subsequent reactions here, but we have a net oxidation that's occurring. But this is how hydroxyl radical is consumed and reformed in these kind of basic tropospheric reactions.